So just to get started, I'm going to start by motivating our work by talking about floating point timing attacks. And so here I have a example website, evil.com. And maybe you went to this website because, someone sent you a link on Facebook and you clicked on it. And one thing, since I am the creator of evil.com, that I can do is I can actually embed an iframe onto the page. And in this example, I've put the BBC website. Now, the same origin policy essentially tells us that you can't access the data within that iframe. I can't just read the pixels from the iframe because those pixels could contain private information. But something else that the browser does for you, which is a little strange, is it allows you to process on the iframe data itself. So for example, right here, I've applied a sepia filter to make it look a little old-timey. Now, what's interesting about being able to process on the iframe data itself is you can give it special types of filters that give you some type of timing information. In particular, we were able to demonstrate an attack where you can essentially read the pixel values by simply timing how long a certain filter takes. And so right here, this was we reconstructed the image of the bee. This took a number of minutes in order to get all those pixels. But as you can see, we were able to show that you can reconstruct this image. These bugs have been fixed when we demonstrated this 3 years ago, but this was the attack. And so the real reason why we see these types of things has to do with variations in the timing of floating point instructions. Okay, so to give you a way of thinking about this, you can think of this blue blob here as sort of the space of all floating point inputs. And if you were to try to find out how long each one of these takes, you could, sort of time these instructions, see what the latency is. You would realize that essentially there's this chunk here of that have subnormal numbers, and they're super slow. And what I mean by subnormal numbers is you can see that some of those values are extraordinarily small. Now, if you know this and you want to fix this problem so that these things execute in the same amount of time, you might know to use the FTZ and DAS flags. And what these flags do is they essentially eliminate the subnormal numbers by sort of replacing them with 0. And in this way, it essentially makes it so that everything takes about the same amount of time. This sounds like a great fix. And this was exactly what Chrome did in order to fix this bug or fix this issue with being able to extract pixels using timing variation. But there's a certain problem with this approach, which is, all right, you've enabled these flags. And then you go call a library. That library maybe, does some processing on the GPU, and maybe it comes back, it calls back into your code, and oh no, the flags disappeared. Someone reset them or something happened where they're just gone. And it turns out that managing this type of CPU state is very difficult. David Kohlbrenner was able to demonstrate that there was a way of actually getting the flags removed so that you could once again carry out that exact same timing attack and recover pixels. Again, they fixed this bug, but it is pretty fragile. And if you were to be very, very careful with your timing, you would realize that there's actually more timing variations than what I just described. So if you were to be very precise, you would notice that there's actually these two regions that are very slightly fast. And what that has to do is the top region, we're dividing by 1. The processor simply knows, well, if you're dividing by 1, you don't need to do anything. So we already have the answer, and it takes little less time. And the bottom case there is dividing by a special value, infinity. This could be nan, any of those. And again, there's nothing to really do. There's no division to perform. It just simply gives the output 0. And this also poses the question of, well, could there be additional timing channels? Could there be something we haven't discovered? And based off of these observations, we can start to think of what an ideal solution would be. And so first of all, most obviously, we would want a solution that's secure. We want to eliminate these timing variabilities. But Additionally, it would be very useful to have some solution that's extensible because there could be future timing channels. And even if we found all of them now, who's to say, Intel comes out with another processor, we get more timing variations that we now need to take care of. Next, we want it to be correct because, one solution, it's constant time, just replace everything with 0. It's constant time, but it's kind of useless. So we want something that's generally correct. And lastly, something that's fast. We don't want to put too much overhead, especially if the browser wants to use something like this. And to address these points, we came up with our system called constant time floating point. And it's based off of 2 observations. The first observation is most people don't need the full floating point range. And we've already seen this, right? When I was talking about those FTZ and DAS flags, they already replace subnormal numbers with 0. Meaning the user isn't going to be using those specific values, and we do take it a little bit further in order to recover speed. The second observation is dangerous values themselves can, generally speaking, be emulated. So, for example, if we're trying to fix the problem with x divided by a nan, well, we already know what the answer is. It should be nan. So we can simply use constant time masks to replace x divided by nan with x divided by 1.5, perform the division, should be fine, and then replace the answer with the expected answer, which would be nan. Great, so I'm going to go into further detail about each one of these, starting by talking about how we eliminate subnormal numbers. So very simply, we can just think about a number line and where the subnormals fall on this number line. They're all really close to 0. And all we really want to do is to take all those subnormal numbers and replace them with 0. And like I said before, this emulates the dnorms are 0 flag. People already do this. And to take a step back to think about a little bit more abstractly, you can think about addition as being an operation that has some inputs, and some inputs here are safe. Some of the inputs here are unsafe, and we're trying to apply some type of fix. And in this case, this fix is underflow that addresses those sets of dangerous inputs. And as a result, we would get some, addition with underflow operation that emulates addition, but is safe on the entire range here. But there's something I've missed, which is subnormals are very special in that they are also slow if you get them as outputs. So to be very explicit about this, I'm just going to give a very simple example. So we have 2 numbers here that are both normal numbers, and we just get an answer that's smaller than the inputs and is subnormal. And so we need some way of essentially predicting when the output's going to be subnormal so that we can deal with this case. So the first way I'm going to talk about how we deal with this is what we call the restricted range, or just restrict for eliminating subnormals. So here's a plot of A plus B, and what I'm going to plot on here essentially is given the A and B is a given output subnormal. And if you were to sort of plot this out, you'd get something shaped just like this. And so if you have an A and a B within an A and a B in that red region, it will correspond to a subnormal output. Now, a very easy way to get rid of these is to just eliminate everything in this blue box, right? It's an over approximation, but the nice thing about this is it's essentially super fast, right? It's very easy to just say everything below a certain limit, just get rid of it. And so by doing this, we get speed, but you might be tempted to say, well, why don't we do something a little bit more precise? Maybe I want to use small numbers, not subnormal numbers, but small numbers. And so for that, we do have an alternate method of eliminating them that we call the full range. And so looking at this plot again, the sort of idea is we want to underflow if A plus B is less than float min, the smallest normal floating point number. Now, you obviously can't run this code, right? Because we're performing the exact addition we need to avoid. But what we can do is use a little bit of arithmetic to try to make these numbers not so small. So we could pick some really big constant C, multiply out everything, and then we get the question, well, okay, we don't have A plus B, that's obviously unsafe, but are all of these operations safe? And one way to think about this intuitively is if you think about some point A and B that is unsafe, right? And it's right there. And what happens when we multiply by C? We're essentially sort of scaling it outward. And if you scale it outward and pick a large enough C, it'll end up being outside that range and therefore be safe. All right. So covering subnormals, we still have to deal with these special values. In this case, we emulate them. We actually want to produce the right answers. So division in particular has a lot of cases with special values. So here's just some of them. So 0 divided by infinity, nan divided by anything. 0 divided by 0 is another case that gives nan. And so the way we handle these is we essentially make a fix for each individual one. In this case, 0 divided by infinity, we know what the answer should be. It should be 0. And so we can sort of fix that little input that is bad. You know, we can also handle the nan divided by anything, 0 divided by 0. And the nice thing about the way we build our systems, you can essentially compose these into one big fix that sort of fixes all of the special values. And because it's composable, this makes it very nice in case later on we discover something bizarre like 1 divided by pi. That takes a different amount of time. Well, we can just create its own individual fix and compose it into the fix for all specials and sort of cover the entire range. And there are some other cases. I'm not going to explain them because they get pretty complicated. It's something that you should read the paper in order to see, because there are additional issues with like dividing by powers of 2, square roots of powers of 4. But for the sake of time, I'm going to move on to verification. So we really want to get these things right. And in particular, there's 2 properties we want. First property is safety. We only want to operate on safe values. What this means is, like, when we do an addition, the addition doesn't get a subnormal as input and it doesn't produce it as output. And then secondly, we want some type of correctness. In particular, if we have safe values, things that don't produce these subnormals, or the work on special values, we want it to essentially produce the correct value. And the way we do this is we essentially just encode our operations into an SMT solver and ask it if we get bad values. And in order to verify this, that we do it in piecemeal. If we were to simply just take all of division, it's a few hundred lines long, and give this to the SMT solver, it would never return. It would just take way too long in order to verify it. So what we do is we essentially verify these things bit by bit. So when we talk about division, similar idea to before, we have some inputs that are unsafe. And what we can do is we can apply a fix, and this sort of transforms it, like before, into a new version of division that removes that bad input. And what we ask is we ask the verifier, is this okay? And it'll tell us, yes, yeah, that's okay. And then we can essentially do the same thing for the remaining, transform it into something until we get this safe final version that we can check. Is it safe? And so what we've done by composing all of these small checks is we've essentially created one big check for a safe version of division where everything's okay. And to really motivate why you want to do verification for this type of a problem, I'm just going to go over one of the simplest cases that we have. So verifying underflow here. So right here is an addition operation, add safe, and all we're doing here is underflowing if something's less than a limit. Essentially just replace A with 0 if the magnitude's less than L, replace B if it's less than L, and perform the addition. Very simple. The safety property that we're looking for here is that this addition operation has no subnormals, and the correctness property is if it's safe, then we should get A plus B. It's pretty simple. And when we give it to the SMT solver, we first check for safety. It says yes, everything's safe, but actually this isn't correct. There's a very subtle problem here. And it's something we didn't notice at first until we ran it through the verifier, and it has to do with -0. You know, Most people don't even realize -0 is a different, distinct number from 0, but in the actual specification, there is a -0, and it has the property that -0 plus -0 equals -0. So essentially, we had to modify this a little bit just to preserve the -0s on the output. And again, this is the simplest case. When we're talking about division, it was back and forth going between the solver and then testing it in order to find all of the mistakes we had made. And with this, now that we're pretty sure we got it right, let's see how we evaluated it. We started off by building an implementation, just a library with all of these operations implemented as functions. And so it's pretty simple. You have restrict, add, full, multiply, so on and so forth. Now, the source language is actually in Haskell. We built a DSL to build up these operations, but from the Haskell, we generate LLVM. The LLVM bit code is what we verify, and from that, we generate the x86 machine code. Then lastly, we also implemented this as a pass. It's really nice because you can essentially just say, run this pass, on my code, and it just replaces every single one of your arithmetic operations with a constant time version of it. So the obvious question is, does this break applications? And we first started by running on the spec CPU floating point benchmarks, and surprisingly, everything passes. Like, despite the fact that we're removing floating point values that you can operate on, it still doesn't affect this. Now, that's a little bit of a artificial benchmark, so we also ran it on the Skia graphics library. This has 1,565 tests, a lot of tests. Now, we do see some failures. And in particular, all the failures we see are actually unit tests on floating point numbers. And most importantly, we do pass all the rendering tests. So despite the fact that they do these small tests on, very small numbers or even subnormal numbers, every one of the rendering tests do pass. So we don't really affect the output of the library. Given that, let's talk about the overhead that these operations create. So to start off, these are microbenchmarks comparing the native speed here versus the speed of CTFP. The first one I'm going to show here is restrict. So you can see that we have about 4 times overhead on addition and multiply. The overhead on division is much higher, and this is because division has a very large number of special cases to handle. It's sort of the cross product of infinities and zeros and nans, and that adds a lot of overhead. Square root, similar, it's not as many special cases. When we move on to the full version, things are roughly 2.5 times slower. Division, obviously still bad, but interestingly, square root is the same speed because there's no difference between the restrict and full version. You actually don't have to restrict the range at all, other than subnormals to get square root to work. Now I'm going to transition to double precision. You'll see that there's almost no difference other than the speed of division. And the reason why you see this is because division takes longer. And so our fixes to division end up having a smaller relative effect. Now, in terms of more of a real world code, in terms of a real program, here's the overheads that you see on the spec benchmarks. You'll notice that, the overheads aren't too bad, 2 to 4 times for restrict, but there's a real big exception here, that being LBM. In fact, the overhead here is almost as much as division in and of itself, and I'm pretty sure that program's not just division operations. And what you end up seeing is, due to the way CTFP will modify the program, first off, it has to run last, because you can't let other optimizations run after it because they might destroy the constant time properties that we put in. And because it runs last, it generates LLVM bit code that the code generator has trouble generating efficient output for. And we've done a lot of tricks to try to get it as efficient as it is. So there is an extra overhead of just bad code generation from these transformations. And with that, that covers everything I wanted to cover. And to summarize, the problem we're talking about here is floating point timing variability. And our solution is this secure, extensible, correct, relatively fast operations on floating point numbers. Thank you.
Lorenzo Di Carli, WPI. Very interesting work. I haven't seen any result that show me that the variability has been resolved. I mean, this is mostly a sanity check. I'm assuming you guys verified that.
Yeah, so essentially what we do is we test a bunch of these value categories and some other random values to try to see the variability, and we see ones across the board. So I could actually show you, yeah, we have a table. It's a little overwhelming for the talk. Oh, no. So this is what it looks like before, essentially. So here we have some values for division, divisor, dividend, and yeah, you see it all over the place. You have some fast ones, you have some slow ones, and after we run CTFP, we generate this table again, and it's just ones. Everything's one, is up to like 5 significant figures and that type of thing. So we're pretty confident there's less variability than one clock cycle. So
okay, thank you.
Andrew from Hopkins. I have 2 questions. Very solid work first. Yeah, like very much. So first is that have you thought about like using, for example, integers to emulate floating point operation? Is that constant as well?
So integers are generally constant as far as we can see. The one issue, we tested this like 3 years ago. So in the original paper where we demonstrated this attack, we did have a like fixed point library that we implemented using integers, and so you can do it. We had to be careful with division because we found 32-bit division could actually exhibit some varying timing variability. But yes, if you wanted to implement, you could implement like the whole IEEE 754 floating point numbers and integers, which would be interesting, but it will be very slow.
Okay. Yeah. I have another question. Is like I know there's another like trend in the timing attack is try to give a like a fake time or add a noise. Like last year have a JavaScript 0 that paper also. So this type approach, how do you think? Like how do you compare with such approach?
I mean, yeah, you definitely could do that. So one thing that was very interesting about that approach is in the original attack, it also attacked the differential privacy database fuzz, which does exactly that, where it tries to add time. And what we were able to show is while they added time for each query for each row, when they did the sum at the end, they didn't like deal with the fact that different floating point numbers could give different timings. And so you need to be very, very careful about when and how you do it, right? Like I guess you could run it on like every single floating point op, but then, I mean, it's going to be very slow. Yeah.
Thank you.
So one question that I had about the correctness condition you mentioned.
Sure.
So you come back to that in the evaluation a bit, but I was wondering for the formal part, you focus on the safe values and you say, okay, then you preserve the semantics. So I was wondering if you can extend that somehow,
yeah.
what you can do formally about unsafe.
Right. So the full correctness formalism is more like, well, if they're safe, then we get the same answer. And then if they're if they're unsafe, like subnormals, then we say we get the answer as if those inputs were replaced with zeros. And then for all the special values, it's still correct. We get the correct output. So yeah, there is more to it, and we do try to preserve it because, yeah, you wouldn't want to get, if you had a subnormal, get a random number. Right.
Okay, is there more questions? Thanks, Mark.